So Thodoris is one of the organizers of the semester already, so thank you so much for that. He is an assistant professor of operation management at MIT Sloan. His work is really interesting because it spans both economics and algorithmic economics in particular, and machine learning. And I think the way he thinks about data-driven processes really nicely bridges in between these two areas, which I think is a very timely type of research. And Thodoris is here for the entire semester, so you have a lot of chance to talk with him. His talk is going to be about how to bridge between the last two talks we saw, which were about stochastic and adversarial bandits. Thank you.
Thanks, Nika, and thanks everybody for staying until now. So in this talk, we are going to take the two previous talks and we're going to discuss how one can interpolate between the two and how one can bridge the techniques that we discussed before. So the general setting is again the Multilayering Bandit setting, where you have the setting works sequentially over capital T rounds. And at the beginning of the round, the learner needs to select a probability distribution across a set of k arms. And each arm gets a reward, and we're going to specify how the reward is, where the reward is coming from afterwards. Subsequently, once the rewards are generated, the learner randomly draws an action from the probability distribution that they committed to. So A of t is the action that we are selecting, and P of t is this probability distribution. And then we are earning the reward for the action that we selected. So we are earning reward of R of A T of t, and we receive what's called the bandit feedback, where essentially we only observe the reward for the action that we selected, but we do not see what would have happened had we selected different actions. Now, what did this CIPRA tell us? CIPRA told us what happens when the rewards come i.i.d. from fixed distributions that depend on the arm A, but are not changing over time. So there is a fixed distribution for each arm. This is called f of A. And at every time step t, the reward that we are getting for arm t is drawn i.i.d. from this fixed distribution. What Hypeng told us was the situation where in this step 2, the way that the rewards are generated are coming from an adaptive adversary, where the rewards can in principle depend on the entire history. And by history, I mean both the algorithm, of course, that the learner is using, but also possibly previous rewards for all the arms, not only the ones that were selected, and also realized actions that the learner selected. So in the one case, the rewards come from a fixed distribution that does not change over time. In the other case, the rewards are a function of the entire history. Now, in this talk, we're going to try to bridge the two. So we have a nice bridge here between the stochastic and the adversarial case. And we're going to discuss how one can think about trying to interpolate between the two. In particular, we're going to address three questions in this talk. The first question is what is called the best of both worlds. How can one derive a single algorithm that simultaneously attains the stochastic guarantee if the input happens to be i.i.d. and stochastic, while also attaining the adversarial guarantee if the input does not happen to be i.i.d. and therefore it is non-i.i.d. or adversarial. In particular, we're going to discuss two different approaches to think about that. The one is starting from a stochastic algorithm and tries to robustify that, while the other one starts from an adversarial algorithm and try to do a more optimistic exploration to be able to achieve these enhanced guarantees when the input turns out being i.i.d. So this is the first question, and this will be the first part of the talk. Subsequently, we're going to go to the topic of the talk, which is the bridging the two worlds, and we're going to discuss what are models that allow us to interpolate between the stochastic and the adversarial extremes. And subsequently, in particular, we're going to also discuss what are algorithm design principles that can adapt to the difficulty that this particular setting has. In particular, I will discuss three different ways to interpolate between these two extremes. and I will mostly focus on the one that Hypen already discussed, adversarial corruption, but I will also briefly mention two other ways that one can think about interpolating between stochastic and adversarial. The last question that we're going to address is how can we take now the design principles that we designed for multi-armed bandits and extend them to apply to settings that are beyond multi-armed bandits. And for example, to settings where that have more complex reward structures or more complex feedback structures when you don't, it's not that you just receive bandit feedback, maybe it's a more complicated feedback to what you are receiving. We're going to try to understand how we can use lessons from multi-armed bandits to address other settings in the spirit also of what Sipra discussed and Hypen touched on in the last talk. So this is the plan. So let's start first of all by defining what is regret. People have, both Sipra and Hypen have already covered that, so I will be quick. Typically what you care in sequential decision making is that you would like to maximize your cumulative reward. So the goal that you have is that you would like to get as much reward as possible. Now, on its own, this quantity does not really help you to understand how well your algorithm is doing. If you see an average reward that is 0.5, you don't know whether it is the case that any arm that you would have selected has 0.5, but there are better arms than that, or whether you really was able to identify the best arm that has this average reward 0.5. As a result, the notion of regret tries to compare to a benchmark, and Hypen provides a very nice discussion about this, the definition of regret, when it makes sense, when it doesn't. But generally, regret, what it does is selects as benchmark the best fixed action in hindsight. So at the end of the game, you should not look back and regret the fact that you did not use a single action throughout the whole time. Now, this compares to the hindsight optimum. It obviously depends on the realized rewards. As I stated, it's a random variable that depends on the realized rewards. And also depends on the algorithm in the adversarial bandit case, because the rewards, as we said, is a function of the entire history. Now, another notion that is used often is what is called the pseudo-regret, that rather than comparing to the reward, the exposed or hindsight reward of the best action, it compares to the ex-ante optimal action. So both in the stochastic and the adversarial case, one can think about, one can evaluate, if they know exactly what the reward generating process, one can evaluate what action has the highest expected reward. Pseudo-regret compares the expected performance of the algorithm to the expected performance of the reward of the arm that has the highest mean in ex-ante. So, and again, I should say that this still depends on the algorithm, because as Hypen nicely discussed, the rewards are a function in adversarial settings. The rewards are a function of the algorithm. So that's a useful thing to keep in mind. Okay, so with that, now that we have defined the regret, let's move to the two words. So in the stochastic bandit world, as we said, the rewards are i.i.d. for each arm. So each arm has a fixed distribution FA. Rewards are drawn from this fixed distribution. An example that you can think for that is online advertising. So you can think of the arms that we have been discussing as alternative ads that you may want to select if you are Google or Meta or Bing for a particular query. And now the reward has to do with the click probability. What is the probability that, what is the likelihood that if you display a particular ad, this is going to result to a click. And if we think about pay-per-click auctions, this will mean that the platform is going to get revenue. And the mean in this case is what's called the click-through rate, which is the probability that a particular display will result to click. So as Sipra discussed, there are multiple algorithms for this case. Sipra focused on UCB and Thompson sampling. There's also a very nice algorithm that's called successive elimination that we are going to discuss in this talk, because it will allow us to do a more easy bridging towards the adversarial case. it's very similar with UCB, and I will discuss it afterwards. So these are some examples, and the type of guarantees that we are getting, as Tsipras said, is essentially something like logarithmic over the gap. There is a subtlety between in pseudo-regret, you get exactly what Tsipras discussed. For high probability, you will get the minimum of this log over gap and the square root of t, because if the arms are really close to each other, you will have some fluctuations and you will not be able to avoid the square root of t in this case. Now, in the other extreme, when we go to adversarial bandits, again, remember that the rewards now are a function of the entire history. And an example that you can think, as Hypen discussed before, is learning in games. So if you play against other agents, then you cannot really assume that their behavior is going to be completely i.i.d. They may try to use whatever you did against you, for example. So it can even be adversarial, but definitely it's not completely i.i.d. So the adversarial setting is definitely well motivated in such settings where you expect that there will be reactive behavior from against based on what you're doing, the adaptive adversarial case. Now, algorithms in this case, as Hypen discussed, are XP3. That's the one that uses mirror FTRL with negative Shannon entropy. The Charlie-Simph algorithm that Hypen briefly mentioned at achieving the min-max guarantee for the adversarial bandit case, and also the log barrier that we discussed before us giving small loss guarantees and having all the other nice properties that in extending in other settings. Now, the performance guarantee in this case is that you get square root of kt pseudo regret, and for high probability regret, I'm actually not completely sure whether you can get square root of kt without the logarithm, but you definitely can get square root of kt times log t. But yeah, cool. Okay, so that's the two settings, the two words. Now, the first question that we're going to address is the best of both worlds question. Remember, the best of both worlds question says that you want a single algorithm that simultaneously will achieve the stochastic guarantee if the input is i.i.d. and also achieve the adversarial guarantee if the input is not i.i.d. As I said, there are two approaches of that. There's the stochastic-based approach, that essentially starts by running a stochastic bandit algorithm and occasionally tests whether stochasticity still holds. Now, if the test is failing at any particular point, if the test fails, then this algorithm switches to an adversarial bandits guarantee algorithm. So that's the one approach, and we're going to discuss that. The other approach is the adversarial bandits approaches that run an adversarial-based algorithm, and they use different ways in order to be able to achieve enhanced performance if the input is i.i.d. For example, one particular way that you can use is to adapt your exploration based on the empirical gap. So if you have seen that an arm has been significantly worse than another, then you play that less, you adapt you have a larger learning rate, for example, in this case, or some different exploration parameter. Okay, cool. So let's start with the stochastic-based approach. So in the stochastic-based approach, we have one algorithm that is used is, for example, successive elimination. This is an algorithm by Evendar, Manor, Mansour, and Mansour from JMLR 06. So we have two arms. The one arm has mean 0.4 and the other arm has mean 0.6. So, and what we do is that we keep a set of active arms at every time. Initially, all the arms are active, but as the algorithm will proceed, we are going to deactivate some of the arms. Similarly, with what Tsipras said, we are going to keep a confidence interval around each arm, because as we said, the greedy approaches will fail typically. So you're going to keep a confidence interval around the mean, around the empirical mean of the arm. So by the green here is the empirical mean, and you keep a confidence interval. You add and subtract a bonus to ensure that with high probability, the actual mean will be inside this. Now, how the algorithm works is that at any point, it selects an active arm uniformly at random. When you select an active arm, the confidence interval shrinks, because if you see how the bonus is defined, it has, in the denominator, it has the number of times that you have selected that, which is similar with what we saw in UCB. And once an arm is dominated by another arm, so once the upper confidence bound of arm 1 is below the lower confidence bound of arm 2, we're going to eliminate or deactivate this particular arm, and we're going to remove it from the active arms. Now, the crux of the analysis is similar to with UCB. With high probability, the actual mean of the confidence interval is always within the confidence interval by concentration bound, by the similar hefting bounds, for example, that Cipra discussed. And one can show, similarly as in UCB, that that any suboptimal arm is going to be deactivated after log T over gap squared rounds. And this means that you're going to get log T over gap squared times gap, because every time that you're selecting this suboptimal arm, you get a suboptimality gap, which is the difference between the optimal mean and the mean of this arm. And therefore, you get this log T over gap regret guarantee. Now, the stochastic-based best of both worlds approaches start with successive elimination. And what, for example, the original paper of Bubek and Slivkins that introduced the setting, this question of best of both worlds, did was that they ran successive elimination. And at any point, and what they did for deactivated arms, they randomly tested if the rewards are consistent with the confidence interval. So what can happen here is that after some time, you deactivated some arm. This arm may have been the arm that is the best arm because the input is adversarial, for example. And therefore, you're going to test to make sure that whatever you have seen before is still representative for what is the performance of the arm. And if not, if the test fails, so if you detect non-stochasticity, then you're going to switch to XP3.P, which is a high probability adversarial bandit algorithm. The guarantee that this gives is k log squared T over gap stochastic pseudo regret, and also square root of KT. This is square root of KT for the adversarial regret. Now, in designing the tests, the main subtlety is that you need to make sure that the tests are not too frequent, because if you are testing too often, you will lose the logarithmic guarantee. You don't want to select suboptimal arms very often if it is the case that the input is stochastic. The whole point is that you only going to get logarithmic guarantee in that case. But also they should not be very infrequent either, because if you detect the non-stochasticity after you have already lost square root of T, then you're not going to achieve square root of T afterwards. So you need to make sure that you need to balance the two, essentially. And that's the main challenge in this case, and the design of the testing that Bubek and Slivkins is doing tries to balance those two. Now, subsequently, there was a paper by Peter Auer and Xiang, which provided an alternative version, which is called the stochastic adversarial pseudo-optimal algorithm, so SAPO rather than SAO as before, that showed that in fact one cannot improve on this log squared T unless you get a linear regret in the adversarial case. So that if you care about high probability guarantees, this log squared dependence is unimprovable. That said, what they did is that they designed an algorithm that had an adversarial pseudo-regret guarantee of square root of KT and a log T guarantee for the stochastic pseudo-regret. And the key idea in their case, in order to improve this log square to log, was to use what we learned in the previous talk about negative regret. So the idea was that because when you are testing, if you continuously see that an arm is worse than another arm, then if it turns out that this arm was better, you have accumulated a lot of negative regret because this arm has been worse throughout this whole time. So you can use this negative regret to make sure that you will do less testing in this time if you have already accumulated enough negative regret, and therefore you are going to do less exploration, which is going to give to the improved log T compared to the log squared T. Yeah, sure.
So these delta is the min of all delta i's. Is that significant, or are you just using an approximate?
Mean, yeah. In this case, I'm using the mean. I believe that the bounds are not expressed as sums. They are expressed as k over delta. In both cases, the delta is the minimum gap.
So it's not possible to get sum over I, 1 over delta I?
I believe that these two papers do not give that. Yeah, I'm not sure if this, if you can get it.
Pseudo regret is usually defined to be, the regret against the best armed expectation in the stochastic setting. What does it mean in the adversarial setting? I didn't quite get that.
So remember how we defined the rewards in the adversarial case? We said that the reward is a function of the entire history.
Right.
So essentially, if you think about all the possible histories and based on the algorithm, the algorithm will generate histories.
Right.
And therefore you can take expectation, you can see which has the largest reward. This largest expected reward will be the benchmark that compare the pseudo regret in the adversarial case. Again, this is the comment that Hyben said before as well. This is a function of the algorithm. In the stochastic case, it is not a function of the algorithm. Okay. Other questions? Yes.
I hear that the regret is linear into.
Yeah, sorry, this is a typo. This should have been square to 50.
Oh, I see.
Yeah, so.
Could you give some intuition of what the testing strategy is in either one of the?
Yeah, so the things that you typically test are the following. The first one is that you test, so you have created the confidence interval, right? For the arm that you eliminate. You test that the rewards that you see are not away from this confidence interval. This is one thing that you test, and this is typically mostly what this paper tests. This paper also tests whether the reward that your algorithm is getting is what you are expecting based on what you have seen essentially. So also testing whether the arm that you converge to essentially really satisfies that as well.
But then you're not testing the suboptimal arms very much.
You are not testing the you're testing the suboptimal arms to make sure that they are still within their confidence intervals essentially. So you want to make sure that essentially whatever you estimated is accurate for the setting, for the future essentially. That's the high level idea. And you do that over different intervals to make sure that over different intervals essentially they are still the estimate that you created based on the initial exploration phase is still consistent with what you're seeing. Yes.
How do you choose which arm to test, and what's the order of the frequency for such test?
So this is so in this case, for example, what you do is that you have multiple different phases. Once an arm, so initially you think about all the arms have uniform probability. Once an arm is eliminated, you decrease by half the probability and you test it with this probability. Now, if this still has the same losses, it means that you accumulate negative regret worst case. So you decrease the probability by half, and this becomes 1/4 of the default. Now, like if it happens now that this arm actually now you have gets positive regret, then you say, okay, we'll bump up again to half. So that's essentially the scheme of how to test, for example, the sub-arm. Okay.
Just one question, yeah. So this k over delta, like the worst delta, depends on the worst delta. Is it something fundamental, do you think, or is it just because they didn't bother to make it some more?
My understanding based on the algorithm is that you should be able to get summation of y over delta summation of y over delta, but I'm not completely sure. Yeah. Okay, so this is stochastic based approach. Now let's move to the adversarial based approach. So the adversarial based approach starts with an adversarial algorithm like XP3 and tries to make it attain the stochastic guarantee as well. So the adversarial based approach started by the paper from Yevgeny Seldin and Alex Lykouris in called 14, and subsequently Seldin and Gabor Lugosi improved the parameterization in this case and improved the resulting guarantee. So what are they doing? They start with XP3, which is the algorithm Hypen discussed, and XP3, one version of XP3, mixes with a uniform distribution to ensure that you are going to do enough exploration. Now, what is the observation in this paper is that rather than doing a uniform exploration, you can try to adapt the exploration that you're doing on the empirical gap. So if an arm has been worse, you are going to explore it less often. Now, this is not going to cause a problem, a significant problem, because you still use importance-weighted sampling in the XP3 algorithm, and therefore, whenever you see a high, you explore it, you are presumably going to see a high loss, and then estimates that you're getting are unbiased. So this algorithm leads to near optimal stochastic and adversarial regret. Now, the optimal guarantees, this is working. Okay, now it's working. Now, the optimal guarantees come from the paper from Haipeng and Chen Yu initially, and the real optimal guarantee comes from Zimmer and Seldin. So, and the idea is that not use XP3 as your basis adversarial algorithm, but rather use either Chalice or log barrier, as we discussed before. And now these algorithms do not do a direct gap estimation, but they are exploring significantly more fast. So essentially, they end up identifying the suboptimal arms significantly faster. So it's still the case that the weights of suboptimal arms decrease more starkly, and this allows them to get an enhanced guarantee. Now, the analysis goes by bounding the regret by a self-bounding term, and you use this is a unified analysis because you use the same self-bounding term to bound both the stochastic and the adversarial case. We are going to have Julian Zimmert actually in the September workshop. He's going to talk about Chalice. He will have 45 minutes to talk about Chalice, so I will not give more information about that now. Julian Zimmert is the author of this paper. He will be in the September workshop, and he will give a 45-minute talk about Chalice. Questions? Yes, Zip.
So just to clarify, so the X3++ and then the SAO algorithm type algorithm, those are both kind of like stitched together, whereas this last one you're talking about just is an adversarial algorithm that just naturally also works stochastically because it explores enough.
Yes, so the Chalice and log barrier, if you do not make any change on the algorithm, I guess in the log barrier you have the schedule plays some role, right? In order to achieve the learning rate changes in order to achieve. So there is one small change in the log barrier case, and yeah, like while the other one essentially you try to stitch the two. Essentially, in the one case you have a stochastic bandit algorithm, but you do tests in order to switch to adversarial. In the other case, you start with an adversarial algorithm, but you play essentially the exploration, how you're going to explore according to some stochastic driven parameter, which is the empirical gap.
And so it seems unlikely, but are there sort of similarly like any stochastic algorithms that just naturally do okay with adversarial? That seems far-fetched, but
no, this cannot really happen because the way that and actually we are going to discuss that when we talk about corruptions. But the way that you can think of it is that the stochastic algorithms end up not selecting the suboptimal arms after some time. UCB, for example, is completely deterministically stops selecting. Even Thompson sampling really has converged in a situation that the two are very well separated. So you will not be able to start from a stochastic algorithm without changing anything and get it directly.
That's convenient on the stationary distribution. If you have distribution is changing, you might end up with a UCB that doesn't solve it.
Okay, what I'm saying is that the classical UCB or the classical successful elimination or the classical Thompson sampling, I believe, we're not expecting them to give such a guarantee. Of course, one can design algorithms that have this property. Chalice in particular has this property. But yeah, stochastic. Yeah. So essentially, the idea of stochastic algorithms tends to be that you initially explore to identify the optimal arm. So this means that you're not going to select the suboptimal arms. Of course, there may be cases where one can design more clever algorithms that have this property, and yeah, we can discuss that. Okay, so this completes the first part where we asked the question of best of both worlds. How can we achieve an algorithm that simultaneously attains the stochastic guarantee if the input is stochastic, and also the adversarial guarantee if the input is adversarial. Now, what are some challenges that exist with the best of both worlds mindset? First of all, if we go to stochastic-based approaches, what they tend to do is that they switch to XP3 if they detect non-stochasticity. So even if you have a minor amount of non-stochasticity in your data, you will go to something that is completely adversarial afterwards. The second challenge is that until recently, and this point does not apply to Charlie's, adversarial-based approaches analyze stochastic and adversarial in a completely different way. So it's often you will need to analyze, to incorporate techniques of the one inside the other, essentially. And finally, a point that applies, I believe, to all the adversarial bandit approaches is that if you go to more complex settings, for example, you go to more difficult feedback structures that are about binary feedback, for example, or you think about other reward structures that are not decomposable across elements, it's not clear how you have, it's not clear how you get an adversarial bandit algorithm. So it's not really clear how you're going to even start an adversarial-based approach because you don't have the backbone of the approach, the adversarial algorithm. So this brings us to the two other questions that are combined. The first one is the bridging the two worlds, which says, what models allow us to interpolate between the stochastic and the adversarial extreme, and what are design principles that can adapt to the difficulty of these settings. And then the related question is what happens beyond multi-arm bandits. How can we extend such principles to more complex feedback structures and more complex reward structures? Now, in a paper with Vahab Mirokli and Renato Islam a few years ago, we introduced a model that we call stochastic bandits with adversarial corruptions. And the idea in this case is that most of the data are i.i.d, but some rounds are adversarial corrupted. Now, the examples that you can think, in online advertising, there's this phenomenon that's called click fraud, for example, where an advertiser may create a bot and deliberately not click some particular ads of the competitor in order to make sure that their ad is going to be the one that is selected. And so therefore manipulating what the platform learns. If you think about recommender systems, you may have a bunch of different fake reviews that may affect the estimates that you're getting. In all of these systems, the platforms tend to try to identify suspicious activity. So we can expect that part of the corruption that exists in the data is going to be identified, but some of it is going to remain undetected. And the question is, how can we make sure to have algorithms that will be robust to the amount that remains after that? Now, what is the formal model? This is exactly the same thing that we discussed before. So the learner selects a distribution PT across arms. Each arm gets a reward. The learner randomly selects arm AT, earn the reward of the arm they selected, and observe the reward, the bandit feedback, observe the reward of that arm. Now, the change that we're introducing is that we are allowing at this step an adversary to select whether the round is going to be corrupted or not. So the adversary selects a variable C of t that can either be 0 if the round is not corrupted, or 1 if the round is corrupted. And this is an adaptive adversary. Similarly to before, they can make the decision as a function of the entire history until this point. They do not know the realization at this particular round, similar to the adversarial case, but they know the algorithm and they know whatever happened in previous rounds. Now, the reward is either drawn from the stochastic distribution if the round is not corrupted, or it is coming from coming from an adaptive adversary that can depend on the entire history if the round is corrupted. And other than that, the same is exactly the same. So does the model make sense, of course? So it's exactly the same thing as before. We allow an adversary to corrupt or not. And if the round is corrupted, then you see an i.i.d draw from the fixed distribution. If the round if it's not corrupted, if it is corrupted, then it comes from an adaptive adversary. One can refine this. This presentation by allowing by talking about guarantees that will scale with the amount of corruption that existed, but this is the simpler way to present this case where an entire round is corrupted. Simpler.
So I
Are we
was
saying that
wondering, like,
adversary's reward is sampled from an adversary sequence?
Sorry?
This distribution is RA star sampled from a distribution determined by adversary?
Yeah, so I mean,
That question.
you can, yeah, so the question was, is the reward, the array bar coming from a distribution? This is one way to formally define what an adaptive adversary means, that the adaptive adversary selects a potentially randomized function that depends on the exact whatever has happened until this point. For any possible trajectory of whatever has happened until this point, they select a randomized distribution, so it's a randomized reward. So if in that sense they sample from this case, but it's not a fixed distribution. It's just a formal way to define what an adaptive adversary means in this case.
Does the adaptive adversary even need random?
No, there is, but they are allowed to, I guess, is what I'm saying. Yeah. Yeah.
yeah, so I was just wondering, like, if I think of observation error, I would think that you observed incorrectly, but the reward is what is the real reward. So the observation would be the corrupted one, but the reward is the real reward. Does that saying make sense, or is that,
So in the paper, we actually discuss both models, both the case where you earn the uncorrupted reward and the case where you earn the corrupted reward. Most of the results have a linear dependence on C anyway.
Okay.
So if you think about rewards being bounded, if we are assuming, then the bound will be the same. In this case, both settings make sense. Like for fake reviews, you don't really care about the fake reviews. You only care about the ones that are the real ones. Yes. Yes.
Shipper's setting, I don't understand why do you pick up the extra linear C if the corruption only appears in the feedback, the way that you measure regret, you just don't pick up any corruption at all.
Yeah, what I'm saying is that if you have a guarantee that anyway has a linear dependence on C, the two objectives will have a difference on this C. So whatever guarantee you have will escape. Now we are going to discuss that in settings in the corrupted objective. In this objective, one can actually achieve, in some cases, guarantees that do not have this linear dependence on C. While the linear dependence on C is unavoidable if you think about the uncorrupted objective, because it could be that the initial rounds are completely not useful. So the goal is to design an algorithm or general design principles that adapt to the number of corrupted rounds. So capital C will be the total number of rounds that are corrupted. Now, what I will try to do in most of the rest of the talk is to discuss three main techniques that achieve such a nice interpolation, essentially, such guarantees that will be robust to C, that adapt to this amount of corruption. Yes.
I thought C was the L1 or like the total amount. Is it
Yeah. So again, I meant this comment before. So for this talk, for the purpose of this talk, and also in many other settings, if you think where there is no scalar notion that is associated, you need to define C as the number of corrupted rounds. In multi-arm bandits or reinforcement learning, you can actually define them as L1 norm between the i.i.d draw and the resulting corrupted draw, essentially. Okay, so the first algorithm is the initial algorithm that we introduced in the paper with Vahab and Renato that has a log squared guarantee, which, if you remember, is similar with what the SAO algorithm was having for high probability. And we said in this case that log squared is not improvable for the best of both worlds case. We have a similar lower bound that actually shows that it's not improvable in the corrupted case if you care about high probability guarantees. And it has a dependence that C is C times K times log T over gap. This is the stochastic case. Now there was a follow-up paper by Anupam actually, and Koren and Talvar that moves the CK outside. So you have CK plus the summation of log squared over gap. And it's also a high probability guarantee. And lastly, there is the Charlie-Simph algorithm and the Charlie-Simple algorithm achieves a guarantee that is the stochastic guarantee plus a term that is square root of C times this. And essentially, as you see, if you think about the gap being fixed, for example, this allows you to get something that would be square root of T in the worst case. So actually, Charles achieves a complete interpolation between the two settings. It does do that for the pseudo-regret guarantee, and it does not extend to high probability, to the best of my knowledge, but it achieves this interpolation between the two extremes. Now, I will discuss all of these approaches in more detail and compare them, and also discuss in which settings the one is more useful than the other. But first of all, let's start by the point that we discussed before about why stochastic approaches fail. Arad. Yes.
So in the case in adversarial bandits, you can get square root C.
Yeah, so there were, I will discuss a bit afterwards. There is a follow-up paper by Masoudian and Seldin in Talk 21 that improves a little bit this dependence inside. And there's a paper by Ito in NeurIPS 21 that also provides another rather improvement, an additional improvement. I'm not sure if they resolve the log T, but there have been some results afterwards that improve essentially some of the dependence inside here. I'm not completely sure whether the log T has been removed though.
And somehow all these results only depend on the number of corrupted points and don't depend on the actual character of the sequence. Like if it appears like only once or something like that.
Yeah, and all of these results in reality only depend on the amount, on the L1 distance between the corrupted rewards and the actual rewards. So in reality, it's even more refined than that, but they do not assume, they do not make any assumption about when corruptions happen. And this gives me a good bridge, because we're talking about bridging here, to discuss why the stochastic approaches are real. Because exactly this, if you were an adversary in this setting and you wanted to attack a stochastic bandit algorithm like successive elimination, what could you do? So one thing that you can do is that you can corrupt the exploration rounds. So the successive elimination really in the beginning just selects all the arms and tries to create confidence intervals. Just corrupt these logarithmic rounds in the beginning, and then what you got is that you return for the optimal arm rewards of 0. So you believe that this arm is really suboptimal. It really has a mean of 0. So what breaks here from the previous analysis is that the actual mean is not now inside the confidence interval. And after a logarithmic number of rounds, we actually deactivate the optimal arm, which means that with only a logarithmic amount of corruption, we cause linear regret. So this is a challenge essentially, and this brings back to the question about like this model allows us to corrupt any arbitrary part of the sequence. In particular, for classical stochastic algorithms, this typically would be in the rounds that are more exploratory. Does it make sense, this example? So essentially, what you're going to do if you know that an algorithm does explores and does exploits is just corrupt all the exploration, make the learner believe that the optimal arm is really suboptimal. The learner will stop selecting this arm from then onwards, and then you're going to continue, and you're going to have the learner get linear regret, like constant regret every round. So this will mean linear regret in total. Now, the idea that we're having in what we call multilayering successive elimination race is that let's start from a simpler case where you know how much corruption exists in how much corruption the adversary is going to put. Let's say, for example, that the adversary is only going to put a logarithmic amount of corruption. Now, if you knew that the adversary, this is something that we're going to remove afterwards, but let's as a thought experiment, let's assume that we knew that the adversary really is only going to corrupt a logarithmic number of rounds. So this is similar to the attack that we said before, right? The adversary only corrupted the logarithmic number of rounds in the beginning, and then we learn something completely long. So what can we do in this case? Well, we could update our bonus to take into account the corruption. So you just add a term that is C bar over the number of plays. Which means that even if the adversary was putting all the corruption on exploration rounds, you still have this buffer that allows you to make sure that you're not going to get penalized by that. Now, this, and if you think about the regret, because we said that the C bar is a logarithmic amount, then you had a logarithm, you add one more logarithm, so you lose one constant, but the regret guarantee is the same. Of course, this can only handle a logarithmic amount of corruption, and that's not what I promised you. So the idea, in order to extend that to the unknown corruption setting, is to create multiple independent copies of successive elimination, each of which will be responsible for a different corruption level. So the Lth copy is going to be responsible for a corruption level of 2 to the L. So you have this log T different algorithms that run independently, and each of them is responsible for a corruption level of 2 to the L. Now, at any round, you are going to select the Lth copy with probability 2 to the minus L. Now, if the copy is, and you're only going to update the estimates for this particular, the confidence interval for this particular copy. You're not going to do any update in any of the other algorithms. Now, if it was the case that the index of the copy was above log C, it means that you're selecting this probability 2 to the minus L. So if the total corruption is C, then the expected corruption that you're going to see at this particular copy is C times 2 to the minus L, which is less than 1. And with high probability is less than log T. But we know how to make an algorithm robust to a log T amount. So all these copies are fine. They are slower because you are selecting them with probability 2 to the minus L. So they're going to take 2 to the L time longer in order to identify the arm A star, the optimal arm. But they are going to identify that, and they're not going to be fooled by the corruption. Now, the smaller copies, the L's that are less than log C, will be prone to corruption for the same reason that we discussed before. So the challenge that exists is how can we have a race across these copies that combines the learning speed of the fast layers with the robustness from the other ones. And the idea is that we're going to use the robust copies to supervise the faster ones. And one way to do so is that if at any point a robust copy tells you that an arm is suboptimal, you transfer this information to all the copies that are above them, because you should not trust them more than the robust copy. One thing that can happen is that a copy now may have 0 active arms, in which case you will just go to the first arm, the first copy that has active arms, and you're going to use that in this case. So this is what we call nested eliminations. And essentially, by doing so, the number of rounds that a suboptimal arm is going to survive is dictated by the first robust copy. Because at some point, the first robust copy is going to eliminate this arm or deactivate in the language that I used before. And from then onwards, no copy before it is going to select it afterwards. So the regret that you're getting is C times the regret of the fastest robust copy. And the regret of the fastest robust copy is log T over gap. So that's how you get this multiplicative dependence on C. And the reason why you get the log square dependence is because you run log T copies, and each of them is going to accumulate log T over gap if there was no corruption. So that's how you get log square T plus C over gap, C log T over gap. So this is a high level idea about how this approach works. But let's try to think about what we really did in this case. We had a problem that can be solved by estimating a ground truth. The ground truth was the arm that is the optimal arm. So there was an arm that had higher mean than other arms, and we tried to estimate what is this optimal arm. And then we had an algorithm that worked by aggressively refining some active confidence set. This was the set of arms that were not deactivated. And this algorithm is the successive elimination algorithm. Now, the first step that we did is that we made this robust a corruption level of log T, which was very simple in Multilayering Bandits. And then we had this multi-layering idea where we ran independent log T independent copies of this algorithm, and we used robust copies to supervise non-robust copies. The way that we phrase that, this is actually a more general recipe. It is not only applicable to Multilayering Bandits. in a paper with Hara, Podimata, and also Krishnamurthy and Rob Sapire, we use the same recipe for the setting of contextual pricing, where the setting is that there is a customer that has a value that is the inner product between a ground truth theta star and a context xt, which is potentially adversarial. And the algorithm that we're using in this case is an algorithm by Ilan and Renato Paes-Leme and Adrian Vladu, which is called projected volume, which is a cutting plane algorithm, essentially. And the challenge in this setting is because you have adversarial context, you only receive binary feedback. You only learn whether the value was above or below the price that you selected. Then you cannot really use algorithms like, for example, the mirror descent algorithms that we discussed before, because you cannot create an important weighted estimator, for example, in this setting. So in this case, actually, the most challenging component is to actually create this algorithm, the algorithm that will be robust to a log T amount of corruption. And actually, okay. And actually, Hara is going to discuss that in the September workshop, and also Hara has a follow-up paper in Code 22 that improves the guarantee that we're providing for some settings of the contextual pricing problem. So if you want to learn more about this result in the September workshop, you will hear Hara talk about it. Now, when we go, so what was the general recipe? We had a problem that worked by estimating the ground truth. This was the optimal arm in multi-arm bandits. It was theta star, which is theta star. You can think of it as it's a vector that says how valuable its feature is. So you can think of theta star as a d-dimensional object where its index corresponds to a different feature. And the theta I star says how valuable it is for the customer to have this particular feature. So the algorithms is effectively were successive elimination projected volume, and we use the same idea here in both settings. There are other papers. So for example, there's a result for assortment optimization by Chen, Krishnamurthy, and Wang that is actually building on Shibra's algorithm that we discussed before, the MNL Bandit algorithm. This is the algorithm that works by refining active confidence sets. And also there is a result for product rankings, for example, that is building on an algorithm for product rankings that is uncorrupted. So this is about multi-layering successive elimination race. Let's move to Barbar, which is the second algorithm. So if you recall what did the multi-layering successive elimination race do? It had these multiple copies and you run them in parallel. So you were selecting the copy L with probability 2 to the minus L. They were running in parallel, and at some point, some of the more robust copies were supervising the less robust copies. And the corruption was subsampled, because if you are a copy that has large L, you are only observing, in the rounds that are corrupted, you are only observing that with probability 2 to the minus L. So the observation that Anupam and Tomer and Kunal had was to try to, instead of having these algorithms run in parallel, work with epochs that are geometrically increasing. And if the input is completely stochastic, actually, you can think of such algorithms as in each epoch, in the Lth epoch, you are aiming to identify all the suboptimal arms that have gap less than 2 to the minus L. Now, the idea was that instead of eliminating suboptimal arms, what Barbara is going to do is that it's going to select them with probability that is inverse to the empirical gap in the previous epoch. So it works in epoch. At any epoch, you only care about what happened in the last epoch. So based on that, you compute empirical means and therefore empirical gaps, and you're selecting them, each arm, with probability inversely dependent on this empirical gap. Now, the idea is that essentially, this is also subsampling corruption. Because if the adversary put all this effort and made sure that you realize that an arm is suboptimal in a particular epoch, then you're going to select it with very low probability. So they need to put even more effort in the next round to fool you again. And by doing this, and by using this idea, actually they are able to get this additive dependence of CK rather than the multiplicative that we discussed before. Third algorithm, Charlie-Simph. So again, as we discussed before, the analysis of Charlie-Simph works by bounding the regret via a self-bounding term, which is optimal for, it gives optimal stochastic and adversarial pseudo-regret. Now, the same analysis actually can be used in the presence of adversarial corruptions, and it can you can bound this term by also adjusting to corruptions if they exist. And so as we discussed before, this actually is strengthened subsequently in subsequent papers. And as Haipeng already discussed, this actually can extend to other settings as well, such as combinatorial bandits and reinforcement learning, because it can be used as building block with other regularizers, also using block barrier as well in many of them. Again, as I said, Julian is going to give a talk about Charlie-Simph in detail in the September workshop, so I'm not going to discuss more about this now. But I would like to compare the three techniques, because I think they have different values in different settings. So what does the multi-layering successive elimination race do? It told you that any setting where you have an algorithm that works with confidence sets, you can, it doesn't matter whether it has binary feedback or it has, it doesn't have an adversarial analog, an adversarial algorithm. If it operates with confidence sets and it refines the confidence sets, as what successive elimination does, or projected volume, or MNL Bandit, or different algorithms for different settings, then you can apply the recipe that we discussed and obtain high probability guarantee at the cost of a multiplicative dependence on the number of corrupted rounds. Now, the Barber algorithm has a very elegant corruption subsampling technique, as we discussed before, because it doesn't just run the algorithms completely in parallel, which can lead to something that can be wasteful, but rather uses this samples with probability that is inverse to the empirical gap, and therefore ensures that the adversary cannot corrupt a particular arm without putting, without spending too much corruption budget. And it also leads to high probability guarantee. That said, the drawback of this approach is that you kind of need some notion of gap. In many settings, you don't have a natural notion of gap in order to be able to sample with probability that will be inverse to the empirical gap. In the contextual pricing setting, for example, there is no clear way of what a gap would mean in this case. Finally, the Charlie-Simph achieves a nice interpolation between the two extremes. So actually, when the C is equal to T, you get a square root of T guarantee up to a log T term that we may be able to resolve whether it can be removable. But it requires to have a way to do importance weighting. So it requires to be able to decompose the reward that you're getting in elements where you can apply importance weighting. And so it's not clear how it will go adapt to settings like binary feedback or when you don't have a finite set of policies. As an example, let's think what happens in episodic RL, and we're going to discuss that we're going to discuss reinforcement learning in more detail tomorrow. But so we have a follow-up paper with Max Simkowitz, Alex Livkins, and Wen San, where we use the idea of multi-layering active elimination arrays. Actually, we use it with a UCB algorithm because we do not know successive elimination versions in reinforcement learning, because those will suffer with in exponential to the episode horizon. And we provide guarantees that apply to tabular MDPs, linear MDPs, gap-based results. So for any setting that you have an uncorrupted setting, you can have an analog for the other setting. That said, it leads to multiplicative dependence on the number of corrupted rounds. Now, there's another paper by Chen, Du, and Jamieson that builds on Barbar. It achieves a dependence that is again additive on the corrupted rounds, but only applies to tabular MDPs, because there you can create gaps. So it cannot extend to linear MDPs and does not give gap-dependent guarantees. And finally, in Charlie-Simph, I believe that one can achieve a perfect interpolation for rewards. So if the losses or rewards can be stochastic, adversarial, or corrupted, you can achieve essentially a perfect interpolation. That says it requires the transitions to not be corrupted, because if the transitions are corrupted, you cannot use importance weighting as well. The way that reinforcement learning works is that you work with Q functions. So in some way, you need to be able to create an unbiased estimator about the Q function of a particular action at a particular state. And if you don't have a good idea about what is the future, the transitions, this is not easily amenable. So this gives an idea about the different settings, the different regimes where the results apply, and also in which settings you should think about using one algorithm compared to another. A very interesting thing that I would like to also mention is that there are situations where you have a symbiosis of these techniques. So, for example, there's a recent paper by Chen and Wang, which I really liked, which tries to do learning with inventory constraints. Now, when you have inventory constraints, you have two problems that you need to understand. First of all, you need to understand what is the price that will have you deplete your inventory. So this is a binary search problem in some sense. On the other hand, you also need to define what's the most profitable, price that you could select. So this is a multi-arm bandit problem, because you can think of different prices as different arms. Now, if you use Alice-Inf, as we discussed, this will not work with the binary search type of approach. So you cannot solve the inventory question directly, at least, with a Alice-Inf. But if you use multilayering successive elimination arrays, you're going to get suboptimal guarantee, because the number of arms in this case is something like square root of t, for example, or t to the thirds in these settings, because you need to discretize the space, essentially. And if you have a multiplicative dependence on top of that, then you may have significantly worse guarantees. That said, in binary search, you get log t. So multilayering active arm elimination arrays or successive elimination arrays actually achieves C times log t for the binary search problem. So what Chen and Wang provides is an algorithm that combines the two techniques and uses multilayering successive elimination arrays in order to solve the binary search problem, which is the inventory problem, while using the Alice-Inf in order to solve the inventory, in order to solve the selecting the price question, the most profitable price question, which is a multi-arm bandit problem. So there are situations where actually it's not that you need to choose, but you may want to think about how you can combine the different techniques based on particular characteristics that your setting has. Now, one other point that I would like to mention is that one way to view adversarial corruptions is also as a model selection problem. If you think about what multi-layering arrays is doing, is that it has all these different layers, and each of these layers is responsible for a corruption level of 2 to the L. So in some sense, you can think of them as different models, and you would like to go to understand which model you should trust, essentially, which model to select to use. And actually, a recent work by Chen-Yu Wei and Chris Dunn and Julian Zimmert actually makes this connection explicit and uses the episodic RL work that we had in order, via model selection, to provide an improvement for the corrupted RL problem. And this builds on a model selection approach that Haiben had with Chen-Yu for non-stationary RL. And again, I'm going to advertise that Chen-Yu Wei is going to present this work in the September workshop. So come again in the September workshop. This will have many very nice talks. Now, I promised you that I will not only talk about corruption. So another way that I will briefly mention two other ways to interpolate between stochastic and adversarial case. One way is to think about the memory of the adversary. So what do we say? We say that the stochastic case is that the input is completely i.i.d. This was coming from a reward distribution f, while in the other case, it was a function of the whole history. So there are recent works that try to say that the adversary can only use the last m observations, for example. They have a memory of m. And this makes sense in cases that they have periodicity, for example. Maybe you really care about things. Maybe it's not the case that you're completely i.i.d, but you depend essentially with some way on some of the past rounds, but you don't depend on anything. So there are some results on that line of work by Vidya and co-authors. And Vidya will be here in the September workshop, and she's going to talk both about this and about generally model selection in such settings. Finally, I would like to briefly mention one recent work that we have that also bridges between stochastic and adversarial. So in many cases, the rewards that you're getting are not completely coming from an adversary, but rather come from agents that have their own utility function. They really have some particular objective, and they try to maximize their individual objective. So if you think about pricing, an agent will buy if their value is above the price. They're not going to just select the responses to make you have the lowest possible reward. So these are typically captured well by principal agent or Stackelberg games. In a Stackelberg game, what happens is that the principal initially commits on a randomized action that I denote by xt, and subsequently the agent best responds according to their own payoff metrics. So the principal has a payoff metrics, the agent has another payoff metrics. And there are multiple results for learning in Stackelberg games. So in these cases, the principal does not know the agent's payoff metrics and tries to learn it on the fly. So they select actions, they observe best responses from the agent, they continue by trying to get as much reward as possible. There are multiple settings like Stackelberg security games. The pricing can be written with an unknown demand curve, can be written as such an instantiation, strategic classification. Hara has very nice works in that direction. Now, a crucial assumption that these models tend to do is that they assume that the agent is completely myopic. They assume that the agent will completely best respond according to this, based on their behavioral model. But if you think about settings that are sequential, the agent may decide to sacrifice some of the present utility in order to get something better in the future. So this assumption that the agent is completely best responding often is not something that holds in practice. So in a paper with Nika Hakhtalab and Sloan Ittert and Alex Way, we address how to think about learning with such non-myopic agents. One typical model about non-myopia is that the agent is discounting the future. So the agent has a discount factor, and the total utility that they are getting is a discounted sum of the future rewards. And this, if you think about it, this is again an interpolation between stochastic and adversarial. If the agent doesn't value the future at all, this is exactly best responded, which is a stochastic case. If the agent is infinitely patient, then this is a case which is completely adversarial, and typically you have fault theorems that say that bad things happen in such cases. Now, the approach that we're following is that we try to establish a bridge, again, towards the theme of this talk. So we try to establish an information screen that will slow down the reaction that we have to agents' responses. So this can happen. One way that this can happen is by delaying how you are going to incorporate the feedback that you get from the agents. As a result, if you delay enough, this will mean that the agent will not have a big incentive. They will not have incentive to largely deviate. They're not going to do arbitrary actions. They're only going to do actions that are approximate-based responses. And then we need to design minimally reactive algorithms that are robust to such approximate-based responses. And we do that for all the settings that I discussed before. For Stackelberg security games, actually, we also achieve an optimal algorithm for learning even with a myopic case on the way. And then to be able to, again, do that for an unknown discount factor, we use the multilayering grace that I discussed before to adapt to an unknown discount factor. So you don't assume that you know what is the discount factor that the agent is using. And Sloan is likely going to present a poster of this work in the September workshops. So feel free to see his poster. This gives me a good opportunity to actually remind everybody that we will have a poster session on the September workshop. And the deadline is on Friday. It is for students and postdocs. So if you are a student or postdoc, submit your work. If you're not a student and postdoc, tell your students and postdoc friends to submit works. We get submissions until this Friday, and we're planning to make decisions by next Tuesday so that we tell people to book flights and accommodation. So to sum up, what we discussed in this talk, we took the stochastic extreme from Tsipra's talk, and we took the adversarial extreme from Hypeng's talk. And we discussed how one can try to create bridges between the stochastic and adversarial worlds. we started from best of both worlds, which was the question of how can one design a single algorithm that simultaneously achieves the stochastic guarantee when the input is stochastic and the adversarial guarantee when the input is adversarial. We said that there are two ways to do that. There's the stochastic-based approaches that start from a stochastic algorithm, test on the way, and if they detect some non-stochasticity, to completely switch to an adversarial algorithm. And there is the adversarial-based approaches that start from an adversarial algorithm and try to somehow adapt their exploration based on empirical gap, for example, or do something else that will allow them to achieve a better guarantee in the stochastic setting. Then we moved away from the two extremes and we discussed how to bridge the two worlds. And we mostly talked about adversarial corruptions as a way to bridge those two, but we also briefly discussed memory of adversary and discount factor for non-myopic learning agents as other ways that one can try to go between stochastic and adversarial. For adversarial corruptions, we discussed three approaches: the multilayering successive elimination arrays, the barbar, and the Charlie synth. And we discussed different advantages of these approaches, potential drawbacks that each of them has, and situations where actually you need to have a symbiosis, situations where you actively need to use both of them in order to address your problem. And finally, we discussed what happens beyond you try to move beyond the simple multi-and bandit setting. And we saw, for example, that multilayering race has a general recipe that applies to contextual pricing and non-myopic learning, as we said here, assortment optimization, product rankings, and generally any problem where you have you can create you have an algorithm that works by refining a confidence set that includes a ground truth. We also saw that Charlie synth is extendable in some settings, and this is mostly settings in which you can create unbiased estimates by importance weights, for example, combinatorial semi bandits, reinforcement learning with i.i.d. transitions. And we also saw that this can be used in part as one of the building blocks to deal with pricing with inventory constraints in the symbiosis discussion. And lastly, we said that sometimes actually having this symbiosis is useful. So there are situations where you do not need to choose, but you need to choose which part you're going to take from each of the approaches. And with that, I would like to thank you, and I'm very excited about the semester.
Thank you, Thodoris, for a great talk and for advertising the next workshop. We have time for like one or two small questions. Are there any?
I was wondering, can you give some intuition as to what the hard instances look like for different corruption levels? So is there some general structure to those? Like, so I guess like Haipeng, for example, was talking about like the hard instance for this standard bandits is sort of these two arms getting closer to each other. Then you have, if I fix a corruption level, is there some intuition as to what is the hard instance? Like what's the structure of the hard instance?
So you mean what would be the min-max type of guarantee?
Or like what lower bounds?
I think for min-max type of guarantees, probably the Charlie synth approach will be. Charlie synth, I believe, tries to mimic what the lower bound does for the adversarial case, for the stochastic case. So I think that it may be that it is a similar situation in that case.
I was asking what are the problems with, if I fix a corruption level, what's the hardest problem? So what's the lower bound instance?
Yeah, I mean, I do not know. I would assume that the lower bound will be square root of C. I don't know how the instance will look like, but I would assume that it will be similar with the min-max for the adversarial. For the high probability results, the lower bound that we are providing is very similar with the one that our scan is doing. And in this case, you have essentially you have two arms where you have one or two words, and essentially you need to get C regret if you are in the one world, but like essentially the optimal thing for the one world will lead you to select and one arm half of the times for the initial C rounds. That's why you get the lower bound for the high probability guarantee. For the pseudo regret, I do not have a good intuition about, but I would assume that it's similar with
Okay, is there a burning question left? We have time for a very small one if there's one. Okay, well, the great news is that Thodoris is around. You guys are around, so you can have more discussions. Thank you so much, Thodoris. Thank you so much. So we are starting tomorrow at 9:30 again, and is there there's a reception right now? Okay, well, see you in the reception and then again tomorrow morning. Thank you.